The initial value for the velocity of the car is of course 120 kilometers per hour converted to meters per second. And the initial value for the velocity of the rim of the wheel has to equal the velocity of the car so that there is no slip. The implementation of the forward-Euler method should be straightforward. The topmost subplot illustrates the braking distance. The endpoint of each of these curves is at the braking distance. The second subplot shows that the car velocity decreases almost linearly. This is not quite true of the wheel velocity. In particular, you can see that the wheel velocity quickly decreases to zero when the strength of braking is too high. The most interesting part, however, is the lowest subplot. It shows the wheel slip. If we apply just a little of braking, we are going to run into the lower equilibrium, which is a stable one, and which is always below the optimum value of a wheel slip of 0.2. And you see that for this curve colored in cyan and this curve colored in purple, we do not reach such a reasonable equilibrium. Rather, the wheel locks up. The wheel slip becomes 1, which we've seen in the plot above as well. Among these 5 options, the red one seems to work best. And you see that we must not apply too little braking and that we must not apply too much braking. You may be wondering about this artifact here. Remember how we compute the wheel slip. It's 1 minus the velocity of the rim of the wheel divided by the velocity of the car. If these two get close to 0, their ratio is going to vary wildly. So this is a numerical artifact. So the reason for this artifact is built into our equations. At the end of the simulation, we are dividing numbers which are close to 0. That's always a bad idea when it comes to maintaining stability.